See, we are going to continue our talk on irregular sea waves. So, what we found out in the last lecture is that you can have by Fourier analysis a random wave signal represented as sum of n number of sinusoidal waves. See, this represents this side sum of n, basically here I wrote infinity, but we can make it n number of sine or regular linear waves. See, in other words, the random signal that we had could be thought or could be broken down into n number of sine curves, each of them representing a small amplitude regular wave with a random phase. This is my random phase with a this is my random phase. In other words, phase we have no information on. You are adding n number of waves, one is sin omega 1 t, sin omega 2 t, sin omega 3 t, but the phase means the starting point is different. You know, one is starting from here, another may be starting from here, another may be starting from here, etc., etc. That is what decides the phase. So, we can get that. We can get a random signal by synthesizing that into this. Now, if you look at that, you will see here that this has got the amplitude part. Okay. This has also got the frequency part. See, k is after all connected to the omega, because k, omega square is gk. Therefore, these and these are connected. So, here you have got this. So, I have got omega, I have got this. Both informations are embedded. Supposing therefore, if I took a random signal and if I could find out this and this together, then I will know for which omega what was my corresponding xi a. Earlier, I got what is my height or amplitude, just number of amplitude, that is all. Again, I had separately found out what are the number of omegas, or you can say period or length, but I did not know which wave had how many omegas. So, but in this one, if I did that, you see, I will find say, look, I have got in wave number 1 height so and so of omega 1 so and so, wave number 2 height so and so omega 2 and so and so. So, I have the information of both. Okay, this is number 1. This Fourier analysis therefore tells me that the component waves, when I break it down, each has a corresponding length or period and a height. Only the phase I do not know, that is one point. Second point is we should try to think in terms of now physics, energy. See, now what happened, earlier I mentioned a wave energy per unit of surface area is proportional to xi a square, amplitude square. Okay. In fact, yesterday we have had the formula half rho g xi a square is to be the your energy. Now, look at this part of how a ocean wave gets generated. Now, you see there is a ocean, I just draw a ocean surface, there is a typical ocean surface, some part, large ocean surface may be there. Now, wind blows, okay. As wind blows, from where wind blows that we do not know, or some depression somewhere, etc. This is all connected to solar energy somewhere. But as the wind blows, wind imparts some energy to the water surface. Certain part of energy gets absorbed by the water surface, and therefore, the water begins to move up and down and begin to form waves. You will find out that if you take a bucket of water and if you did, it ripples. If you give a larger one, you have larger height. So, more energy you give, more energy gets transferred. Now, in this kind of sea description, what we are assuming is that we assume this over a distance called fetch, over some 100 mile or so distance, a wind has been blowing continuously for several hours. This is what we are describing here, what is known as a fully developed sea. Why I say fully developed sea? It means that wind has been blowing for quite some time there. So, therefore, whatever energy the wind has to impart, so whatever energy from the wind the water could absorb, they have already absorbed. It's at a saturation level. So it has now created certain waves. So you can assume conversely that the energy of the waves remains constant for a given wind speed or a given wave state, because energy is a conservative principle. Now see, initially it starts, wind starts blowing and certain energy gets absorbed, certain wave form. Now sometime later more energy gets absorbed, but beyond a certain point of time energy cannot keep on getting absorbed, it has got saturated. So and that time I call the sea to be fully developed. Statistically now heights are not continuously increasing, it is now random, irregular, but having a statistical average. Okay. This is what is called a fully developed sea, and we are describing here. Why I come to this point? The main point is here that I want to describe where if I took this random signal and break it down in components, per unit area energy of that surface remains constant, because energy is conservative principle. If wind was blowing at say 20 knots for a long time, then the wave that has got created would be of such a nature where the total area over a certain certain surface area, unit surface area, remains constant. It may look different, it may have a different kind of distribution. It may like today it may look something like that, then it may look random.
But sir, according to the wave, the energy fully what is there, it's not spent, no?
Fully?
What energy it is absorbing and getting?
No, whatever, no, that's okay. It's not the energy of the wind. That's fine. That is not what we are saying. See, nobody knows the mechanism, but what it says is that this is called wind generated waves. Let us say that 20% only gets absorbed. So it is going to be that 20% only. That 20% does not change. So the amount of energy, if there is a wind of 50 knots, let us say a certain x units of energy can get transferred to the water maximum. So it has got transferred. Now wind keeps on blowing and it is only x. Whatever that random wave you find should represent an energy content of x units per square this thing. So although the nature looks random, statistically they should be such that that their total energy is something like x units. This is the point. So the wave looks different today, tomorrow, day after tomorrow, or today and next hour and next to next hour, but they are all more or less having x units of energy. So in other words, the one that I broke down to various components, it should be such that normally that the area under that remains constant. The energy of that remains constant, the energy of that. So this is the principle. Therefore, it would be much better to plot the energy distribution. Energy, see, I have broken it down to various component wave. Again, I will say that I have an irregular signal. I broke it down to a number of certain certain amplitude A plus frequency omega. Okay. Now, if I can plot, instead of that here, see, instead of plotting here amplitude and omega, if I plot here something proportional to amplitude square or proportional to energy, then it becomes much better from a physical point of view. See, I have got this random signal, right? I have got the random signal where I have got this to be sigma of again xi a amplitude into cos omega n t plus etc. So I have got this, I have got this. So I could have actually plotted omega n versus a to find out in a random signal which omega and which a is existing. I can have this plot. Okay. Instead of that plotting, the logic says that plot is less meaningful than to plot on this side something which is proportional to amplitude square, because that would be proportional to energy. Yes. So instead of plotting amplitude against frequency, that is what is called amplitude distribution against frequency, if you plot square of amplitude distribution against frequency, you are actually plotting energy distribution against frequency, energy of component waves. Okay. So what I mean, suppose there is a wave here of this frequency. Now it won't be of one frequency. So all the waves between this to this frequency has certain energy. Now if I plot this this area, so that this area represents energy of all the waves. In other words, this area would represent half rho g into xi a square of all waves between this to this frequency band. That would imply that this is my energy. Such a plot if you make, that is on the vertical side, if you take amplitude square divided by, see, I call this to be delta omega. So, if this shaded area, if this has to be energy equal to half rho g xi a square, then this height s, it is called s omega. S omega then therefore becomes E divided by delta omega, because I have taken delta omega to be this distance. So, if I plot that, that means if I plot, now I will come to the next slide, getting a little confusing here. Instead of plotting, see that what are the options? The option was that I broke it down to number of regular waves. Okay. So, I know what is my omega and what is the corresponding amplitude. I know that. So, I could have plotted omega against amplitude. I could have plotted omega against amplitude. I again come to that. See, I have got broken down. So, I could have plotted number 1 omega versus xi n, xi a. I could have plotted that, but that would be called frequency distribution of amplitudes. But people are not plotting that. But I could have plotted square of that. Instead of that, what I am plotting here, this side is a term proportional to half of xi a square divided by delta omega, where when it is omega, because why I say is that this plot will represent such that it will basically represent the area under the curve between certain frequency band to be the energy of all the waves of that frequency band. So that if you take the entire area would represent the total energy of the waves. Supposing I call this to be, we call it S omega. Okay. Now, if you take, see, S omega d omega over the entire range omega equal to 0 to infinity, what is this? This is going to be half xi a square by delta omega into delta omega, proportional to. This is going to be the total energy. I think it will require a little more discussion. See, once more I will come to that. What we are doing, see, I want to plot here something proportional to energy. What means what? I must plot here something proportional to xi a square. Instead of xi a versus omega, I should put something xi a square versus omega. But if I do just xi a square by itself, what happened? This side can get spread. You see what happened? Let us say I have done the graph for 10 omegas. I broke it down to 10 components. You broke it down to 100 components. Somebody broke it down to 1000 components. If you just plot here xi a square, you see, let us say what I give an example. Suppose I broke it down to 10 components. So, I have got, see, 1 meter, xi 1 for omega 1, xi 2 for omega 2, xi 3 for omega 3, etc. Xi n for omega n. Now, if I just square them up and plot them this side, you see, then if you add them all up together, there will be xi 1 square plus xi 2 square plus xi 3 square, etc., and they will not be same, because tomorrow I can have, instead of n 100, I can have 1000. So, what the convention is therefore is that to plot here something proportional to xi square, all right, but xi square divided by delta omega. Why the logic is, again, in the next one is in a big one, we'll have to go through that. See, I am plotting here. Now, this is here. What I am plotting is half xi square divided by delta omega. What is delta omega? Delta omega is the interval. So, you see, let us see, this is my omega. So, this distance is my. Now, if I plot that, if I plot this, what happened to this area? What does this area implies? This area, this shaded area would be half xi, actually we can call it to be xi omega here, omega square divided by delta omega into delta omega, that is going to be half of xi omega square. Okay. This area is going to be half of xi omega square, which is equal to area. energy, because energy actually is multiplied by rho g will give you the energy. So what I am saying is that if you plot this, then this would be, if you have plotted this quantity, if you plot this quantity, that would represent what is the energy, that would represent a quantity proportional to energy of all the waves of this frequency band, instead of just amplitude square. Now supposing I take this frequency band here, what is this area? This area is energy of all the waves between this frequency band. Like that, if you keep on adding, this entire area under the graph will therefore represent total energy of the surface, water surface. Okay, this is why you have this coming here, or I can call this to be S omega equal to, so that S omega d omega integration of that into rho g gives you total energy. The purpose of drawing this curve is that nothing but an energy distribution, all right, but such that the area under the curve represents the energy proportional to, see, always rho into g is a constant, you do not want to deal with that rho g because it is not a nice number, so you take it out as a constant. So you see, this is very important concept, that you actually are plotting this side essentially the square of the amplitude divided by bandwidth, because you cannot get waves exactly at a particular frequency. So again, if you look back, that what we will be doing, that we have a spectrum, you do Fourier analysis. So you say that wave between omega 1 to omega 2 so many of height so much, omega 2 to omega 3 height so much, omega 3 to omega 4 height so much, you are averaging it all out. So now I know that my waves coming between this to this, all the waves between this frequency band, just like when I said there, all the waves coming between this height band 0 to 1 meter so many times occurring. Here what we are telling is all the waves between frequency omega 1 to omega 2, or omega plus minus a bandwidth, within that, within frequency band, the average amplitude is A. All the waves of this frequency band, average amplitude is so and so. All the waves of this frequency band, average amplitude is so and so. And what I am plotting here is that square of the amplitude divided by the frequency band. Why divided by frequency band? Because by dividing by the frequency band, it makes sure that the area under this becomes the energy of those waves. If I did not divide by the frequency band, then the area would not have become so, because it is even higher. I want to make sure that the area under this represents the energy of all the waves. So this is a very standard representation. It's called energy density spectrum. This is also there in electrical and all other subjects, you see, because it tells me that this spectrum is such a curve which tells me the ordinate will give me a measure of the energy of the component wave. Okay. But area under the curve gives me the total energy, and obviously the area remains constant. Why this area is important? Because now you take this for example. The wind is blowing for long, say 1 full day. Now you took a record for 1 hour today evening 5 to 6 o'clock. You got a record. So you broke it down to various components and you plotted this graph. He did that after evening 9 to 10 o'clock. Now what he gets and what you get are totally different set of supposed to be amplitude and frequency, but the area under that should be same because the total energy is constant. That is the basic philosophy. That although the signal looks different, signal looks widely different, the signal still represents the same energy, and you will find out, we will come to that later on, that the frequency distribution of energy also are actually same. In other words, this graph will remain almost same, whether it is today or whether it is tomorrow in the same place. That I will come to that why it is same later on. But let us first understand this distribution. So wave spectrum, this is called a wave spectrum, or some people call wave energy spectrum, either you call wave spectrum or wave energy spectrum, some people call energy density spectrum, all various terms. I'll next slide write, but this essentially represents a distribution of the energy against frequency of the component waves. So again, if I have to repeat, I have an irregular signal, I broke it down to number of regular waves, and now I have my next job is how I can represent them in a very convenient graph. I could have actually plotted frequency versus amplitude, but people think it is much more illustrative or instructive to plot energy against frequency. But energy by itself cannot be plotted because energy depends on how you broke it down. So, you find out such a way that the ordinate represents a quantity energy by a frequency bandwidth, so that the area under the graph represents energy. This is the main purpose. Okay. So, this thing will now the typicality of this graph. See, now the graph will look something like that. So, this is now S omega, this is we can call is wave, some as I say some people call energy spectrum. So, it is called omega is called S omega. Okay. This is actually proportional to half xi amplitude square by delta omega. This is how this side is, as I said. So, this multiplied by rho into g will give you energy per unit surface area. Again energy per unit, it will have a unit of energy per meter square. We will come to that later on. What is the unit of that? Obviously, it is unit of meter square divided by unit of radian omega, that is this is meter square, no, by 1 by radian, that is meter square into radian, and this is 1 by radian. No, sorry, I am sorry, meter square second, this is 1 by second or radian by second, whatever. You can call r by second, meter square radian by second by radian. Radian having no unit, so it is meter square second and 1 by second. If you multiply, take the area under that, what is the unit? It is meter square. If you multiply this, it will turn out to be the area is the unit of that is meter square. So area under this curve I can call, some people call this to be as M0. You know, by definition you can call this M0. You see, you call the area under the curve to be M0. That is that I will come to that little later on about this M0 and M1 part. Now the question is that this is the most fundamental part, is to therefore realize that I have taken the component waves, I broke it down, and now I will draw a nice diagram try to draw it, where this shows the energy of the component waves. This diagram is given later on, maybe the book will be better. See here, let me try to draw. There is a wave here. I am drawing the component wave. This is one component wave. Next one is you have broken it on this component wave. This here you are representing in this graph. Suppose the spectrum graph is there. This you are representing here. This omega 1. This you are representing. I mean, when I write that, basically the area under that, this is here. See, basically here I have got this omega signals against time. This is time and this is omega. What we have done is that there is a signal which was against time, xi against t, random signal. This, when you sum them up, you have got this. So this signal was broken down to its components. See, this signal was broken down to its components, frequency omega 1 with xi 1, omega 2 with xi 2, omega 3 with xi 3, etc. Now, for each omega, the xi square divided by delta omega is what you have plotted. See, this you have broken it down to various component frequencies omega 1 and corresponding amplitude 1, omega 2 corresponding amplitude 2, etc. So, this can be thought as if it is composed of this frequency with the corresponding amplitude, etc. Now, you are plotting this frequency as the base. This is my frequency base, the amplitude square, a quantity proportional to amplitude square. In other words, what you have done is that whatever you have got xi against t, you have transformed that somewhere into xi against omega. In fact, what you have done is that a signal you had in time domain against time, you have actually represented them in frequency domain against frequency, because this you are plotting against omega versus something. So, this is typically, if one can also say that energy spectrum representation, where a real time a real signal in real time is represented in frequency domain, in frequency against frequency. This is what we have done. This one has been done against frequency. This is the transformation that we have been doing it. So, as long as I can break it down to component waves, I can actually go back the component and just plot the square of this amplitude here. So, if by doing that I get this graph, this is what we call energy spectrum. And area under the, what is area under the graph? It will turn out to be proportional to half in, see, it is proportional to half into xi square. Okay. The area under the graph become proportional to half into the xi n square. I will come to that later on. In other words, area under the graph becomes in proportional to the statistical average wave height square. There is a, it is connected to the square of the height. Now, we will come to this the relations little later on in a minute, but we should understand this part first. Okay, having understood that spectrum, now what we have done is that we have got this spectrum, S omega again omega. Now, area under that curve. How do I represent area? See, there are number of ways of representing area. Let me take this quantity, define moment. What is Mn? Now, you see, tell me what is Mn. Mn represents the nth moment of this area, because see this, see, if there is a graph here, this is x here, this is y here. Okay, integration of y dx is the area under the graph. Integration of x into y dx will be moment of the graph about this line. Integration of x square into y dx would be second moment of area about the graph. Therefore, integration of this ordinate power into y dx, that is y, this ordinate power y to the power n into this dx, this d omega represent nth moment of the curve. Okay. Why I say this nth moment of the curve? Because we will find out that many of the statistical parameters of this graph are related to that nth moment. Now, you see, when you take n to be 0, that means if you take m0, what is m0? It is nothing but the area under the graph. M0 is nothing but the area under the graph, because M0 is S omega d omega. So, M0 which is proportional to energy, which is proportional to height square. So, the M0 becomes proportional to height square. Now, we will come to that this in a minute. This is very important. See, this we must realize that obviously this is true, because what happens now, I took a spectrum, I synthesized that and I found out this graph, and I know now that the area under this graph is supposed to be proportional to the total energy of that random wave. That means if I took in 1 square meter area and I kept on measuring the energy of content of that surface, the energy would be equal to M0, that area under the graph. Okay. And that energy is obviously proportional to the average height square or some statistical height square, because more energy means there will be higher waves, less energy means lower waves. They may not be 1 or 2, but there will be random waves. So, average wave height or significant wave height would increase if there is more energy. So, we will find out later on that this M0 is directly connected to various kind of wave heights. Okay. Let me just concentrate right now on this part. Now, it turns out people, what people have done, people have actually been collecting data. This data, this oceanographic data has been there for ages. People have been for many years, hundreds of years collecting data, and they have been actually synthesizing and they have been plotting this graph. So, suppose it turns out that you plot this graph, say Bay of Bengal you are taking. So, in 1950s you took, 60 you took, 70 you took, 80 you took. Everywhere you take, it turns out that this graph follows very closely a Rayleigh distribution. That again makes sense. Means it is like that, not normal. Means this is actually, the graph will look something like this. Less number of high waves, this is actually more number of this, omega high means small waves. There are more number of small waves there, goes like this. Okay. This is what has been found out. Now, if you can actually have a Rayleigh distribution graph, it turns out that all the statistical formula connected to the average wave height, significant wave height, all possible properties becomes connected to this. That means if you know the spectrum and its area and the moments under the graph, especially area, in fact all the heights become proportional to the area. So if you first of all I have done a spectrum, then I find that it follows Rayleigh distribution, okay, like this. Then I can say that okay, I am going to assume that it follows the Rayleigh distribution, because Rayleigh distribution is a statistical property, some kind of graph. Then I can say if that is so, then the area under that graph M0 can be connected to all statistical property. For example, now we will come to this example. H 1/3 will turn out to become, I will just tell that from here. Don't want to watch. Okay, wait now. H 1/3 will become 4 root M0. Significant wave height. H average becomes 2 root M0. Like that, you know, I just give you an example that it turns out that if the spectrum was following a Rayleigh distribution, and if the area under the spectrum is M0, then the H 1/3, the significant wave height would be 4 times root of M0. Wave height, amplitude would be 2 M0, height would be 4 M0. What happens therefore if I know M0, then I can find out H 1/3. In fact, we can find out all statistical property with respect to all kind of period, all properties, statistical property. All types of height, period, etc. are related to Mn, n equal to 0, 1, 2 typically. That means basically they are related to the area under the graph, first moment under the graph and second moment under the graph. Basically, you know, this is first moment. See, n equal to 1 represents the moment of the graph, and this represents the moment of inertia of the graph of the curve. Anyhow, I will not write the various formulas here, but it turns out that this is how it is. So therefore, lies begins to get sort of simple. So first of all, I have a random signal, then I find out that it is nothing but sum of regular waves. Then if I can find it out, I can find out what omega and what A are associated. Then I plot their graph. It turns out that the graph represents basically Rayleigh distribution. So I make an assumption. Look, I will consider this graph to be Rayleigh distribution. Now I have to find out what is my average wave height or significant wave height. All I will do, take the area under the graph, use this formula. People don't believe it. You take this signal from where you started in the first place, take all the heights there, find out those like what we did before, see the average, you will see that they will match if the signal was Rayleigh distribution. So basically, this is how it now life becomes simple, because any time that you try to take a signal, a record at a location, it turns out obviously today and tomorrow and day after tomorrow they will look different, but you expect their statistical properties same. Here comes the question that I earlier said that, see, suppose this is a one having area same, there is another one is look like that, area is same, another one looking something like this. All of the, this is 1, this is 2, this is 3. All of them the area is same. That means all of them represent same significant wave height. Okay, but they are different because this one is having more number of low frequency wave. That means it will look more low frequency longer wave. This will look more number of shorter wave. This one will 3 will look like that, etc. So they are not the same. So only energy or only height do not tell us, as I said earlier, about the content. You need the frequency distribution. So in this graph, therefore, you know both of them. Now the question is there, if Bay of Bengal in month of July, if I today measured and I got a spectrum like that, should tomorrow also become like that, is the question. The answer is that, just think, what what all parameters might cause the waves to be excited. Number one, wind speed, that is for sure. Number two is obviously the local bathymetry. You see, if you take a particular location and wind is coming from particular direction at particular speed, waves will be random, but you would expect still the statistical quantity of waves to be almost same, because supposing it is creating more number of long waves, you would expect tomorrow also more number of long waves, because they are because of the bottom profile or some kind of bathymetry. So you see the statistical distribution for the same wind speed, you would expect same, just that they look different nature. You would still expect 10 number of 100 meter wave and 20 number of 1000 meter wave. Only thing is that the signal looks different simply because they don't, if you take just sine waves and add the phase differently, you will see that they will look different. See, if you take a sine curve, another sine curve, add them together, you will get one picture. Now you simply shift this sine curve slightly. You shift this sine curve, instead of starting from here, you start from here and add this and this, you will get a different signal. So although you get different signal, they may still represent same energy, because this plus this and this plus this, both will have same frequency, same energy, both of them will have same spectrum, but they look different. Why they look different? Only because their phase is different. So now conversely, in a same location, for the same wind speed, in a same time of the year, let us say, for all the other conditions being same, you would expect that although the signals are different, if you have synthesized them and if you plotted this graph, it will be same frequency distribution. That is very logical to assume, and this is exactly why the spectrum concept is even more appealing, because it tells me the frequency distribution of the heights or amplitudes, and that distribution is more or less constant for a location and for a given wind speed, for a various excitation. After all, if you take, it's a very simple example, if you took a bucket of water, shallow bucket, and give a certain like wind, it gives certain kind of wind. You take a deeper bucket, it may be something else. But if you take shallow water today and tomorrow and day after tomorrow, you will expect same kind of waves. Okay. So this is exactly why this in a given site, when people have taken for a long time, you find out that the signals are same, but the spectrum that you find can be actually similar. And then you find that, number one, you find the spectrum is similar. Number two, you find that it follows Rayleigh distribution immediately. Let me write it down here. Observations so, otherwise we are probably. More or less same, I am writing. So the spectrum is same. Now you find also the spectrum follows Rayleigh distribution. Therefore, you can say that all I have to know is that whether today or tomorrow or day after tomorrow, I end up getting this graph only all the time, because the spectrum turns out to be same. And now I take this area M0 and other moments, and I find out that you see that the moment comes, here comes the question of moment. See, suppose the same area, see, if you take now this graph, you will find that M0 is same for both cases, but M1 is not same. So that's why M1, M2 comes in picture, because if you take one graph, this, another graph, say this, both of them might have same area, but moment will be different. This is exactly why M1 and M2 again fixes up its location actually. So if you have M0, M1, M2 same graph, you will end up finding that as if the irregular C is same. In other words, a random signal, although looks very random, can be statistically same as far as this is concerned. And this is where we are now, that we find out that whenever you are synthesizing them, most of the places it is similar. Now comes the second question. You cannot keep, we are engineers, we cannot keep going and measuring wave heights at every point. What we need is somebody to tell me, look, I have a ship going from here to Bay of Bengal, what is my weather at Bay of Bengal in a spectrum. So people, what they have done is that they have actually come up, no, they have actually fitted this, the oceanographers have been doing that wave modeling and all. They came up with certain what is called theoretical spectrum. In other words, they found out that that this spectrum can be fit to a formula where unknown may be the significant wave height, and so in other words, let me say this can be written as a formula as function of either 1/3 or t, some kind of t, maybe t peak period or something like that, some period. See, there have been number of formula therefore suggested by people that has come up, where you can say you can determine S omega as a formula where the unknown are h 1/3, sometime only h 1/3. Earlier days it was wind speed, but nowadays more of h 1/3, and or sometime this plus some kind of a period, TP meaning, see, this is the peak period. Some formulas are there with only this, some are with both. Both are more common basically. Okay, this is what is called a theoretical spectrum. Why this h 1/3 therefore come in? Therefore, what happens? See, that supposing there is a wind blowing stronger, then obviously you would expect it will be rougher weather. Rougher weather means it would have a higher h1 significant wave height. So therefore, conversely, if you say that if I have a certain place significant wave height of 5 meter, then I can go back to the spectrum and I can put to this formula. A standard formula, for example, I will just write down ITTC formula, ITTC recommended 2 parameter it will look like S omega is 173 h 1/3 square divided by T1 for T1 is some period omega of -5 exponential -692 by T1 for omega equal to -4 etc. when T1 equal to 1.0862 equal to 0.772 TP. So you see, if you know peak period, you can find out this T1. T1 is actually connected to what is called an average zero upcrossing period, one of the period. So what happened, if you know h 1/3 and if you know TP, then you can get T1. Then you can find out for every omega what is S. Any omega what is S. Therefore, you can actually for a given say T1 and given h 1/3, you can find out this graph, omega versus S omega. See, in other words, there is a formula given for S omega as a function of h 1/3 and T1 in this particular formula. So therefore, if you know h 1/3 and T1, they are again connected to each other, then you can find S omega. Now it turns out that oceanographers have also used the word what is called sea state. You know, it's something like if there was more wind, long back it started, if there was a stronger wind for aircraft people, Beaufort, one British scientist or engineer, used a scale called Beaufort scale. He says that if wind is so and so, yeah, I'll call it Beaufort scale so and so. So from that later on, we people like ship people, ocean side people started calling instead of Beaufort scale a sea state. So if we say that if h 1/3 is 5 to 6 meter, my sea state is 5. There is a scale between the word sea state and h 1/3. So now we have got a table sea state versus h 1/3 versus T. So what happened? I want to find out what is my wave spectrum in sea state 5. I go back to the table and find out what is my h 1/3 TP. Then I go to the formula and I draw this graph. This becomes my spectrum for sea state 3. See what happened? I go to this picture. I find out for sea state 1 my h 1/3 and TP is so and so. I go and use that formula. It turns out that actually what happened, the spectrum, as wind blows, the diagram is not good. I should draw it just last and then quit. This, as the wind starts growing up, the spectrum actually begins to shift on this side. In other words, what happened, as h 1/3 goes up, okay, as wind starts blowing more, your significant wave height will be more. You will end up seeing a spectrum which will having more number of long waves. This I will pick up on that a little bit on the next class.
The energy content
Will be also more. So area. So you take two things: small height here and very high wave here. So the area under that is much smaller because obviously area under that is proportional to significant wave height, which is say 2 meter. But there will be more. See, when there is a 2 meter wave, it is all connected. I have got a wind blowing at 10 knots. 10 knots will give me number of small length wave, 50, 100 meter long wave with a smaller height. So average height is less. So the spectrum is shifted on higher frequency side, small wavelength side. As wind begins to blow more, I will have higher waves, also longer waves. So it will shift on this side and area will also become more. This will happen. This has a very significant effect on the ship motion, we will find out. See, small boats are operating in very moderate weather, but they are operating this small sea state. What happens when the typhoon starts to blow? You will have more number of 200 meter long wave or 300 meter long wave. Very long. You will, in one case you will have more number of small waves. Another case you will find much more number of longer waves. You see. So these are the two extremes, and we have to typically that happens. We will discuss more on that in next class. We'll stop today here. We'll do a little bit of this elementary spectrum part also in the next class. Thank you.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology, and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. that ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body. In areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire.
आदर्शाय मादर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. His own immortal words, it is indeed a fine monument of modern India.